¿Listo? Bueno. No, aquí estoy.
Hola, Joaquín. ¿Me escuchan?
Sí,
Sí,
¿Qué tal?
Ángel.
Buenos días. Ya estamos en vivo en YouTube.
Tú nos dices, ¿verdad?
Sí, a las 10 en punto, que ya es como en 30 segundos, en Eventia los voy a poner ya en vivo. Por aquí por el chat les voy a mandar un mensaje de ya estamos en vivo y pues ya harías la presentación del doctor Raúl y ya iniciaría con su conferencia, ¿ok?
y muy bien.
Perfecto. Cualquier cosa la ponen por ahí en el chat y ya lo solucionamos.
Muy bien.
Tú me das la señal, ¿verdad?
Joaquín, yo les doy la señal. Joaquín, doctor Raúl, ya vamos a comenzar. Espero.
Thank you, Ángel.
Bueno,
¿no yet?
we're going live in 3, 2, 1, ready.
Perfect. Welcome back. Now we are ready for our first keynote conference, in this occasion delivered by Raúl Rojas. Raúl, thank you. We feel very honored that you found the time to participate in our conference. Thanks much. And well, also Raúl Rojas is very well known for all of us. I would like to spend some time sharing with you some of his accomplishments. Well, Raúl is graduated from the Escuela Superior de Física y Matemáticas of the Instituto Politécnico Nacional. But he also studied economy at the Universidad Nacional Autónoma de México and obtained his doctorate in economics at the Free University of Berlin. There, he was granted his habilitation in computer science. And in 2015, Raúl received the Teacher of the Year Award, an accolade from the German Society of Teachers. The city of Mexico gave him a gold medal through his head of government, Marcelo Ebrard, in 2008. And then in 2015, Raúl received the National Prize for Science and Arts in the technology category for the government of Mexico. His book, The Language of Mathematics, was awarded the 2018 Science Dissemination Prize from the Fondo de Cultura Económica, and he is currently professor of mathematics and statistics at the University of Nevada, Reno. And well, I would like to add to this list of accomplishments the fact that one laboratory at Cicata Querétaro is named after him. Well, thank you, Raúl, and I would like to pass you the microphone. Thank you very much again.
Thank you, Joaquin, for the introduction, and thank you very much for the invitation to be today with you. I'm going to share my screen, so I hope you can see my slides.
We see your
And when I was invited to give this talk, which is about technology and applications of technology, I decided to give a more like a kind of overview of what's called exponential innovation in technology today. And artificial intelligence plays a big role in these so-called exponential technologies, as you will see. And I wanted to contrast this to show you the difference between this technological revolution and the past technological revolution. So this is what I'm going to do today. And then at the end, we will have time for questions. So if you have any questions, you can post your question to the chat, and it will be read after the talk. So let's talk about industrial revolution. So many people talk about 3 or 4 industrial revolutions. I always like to think just about 3. The first industrial revolution was the one defined by steam power, by the introduction of another source of power different than human power, and also by mechanization of work in the factory. The second industrial revolution was defined by electricity and the internal combustion engine, another kind of energy source, if you want, at the level of the factory. And the third industrial revolution is the revolution of the computer and artificial intelligence. And these industrial revolutions, they have consequences. Here you see from the Economist the yearly growth rate in several countries, Britain and the United States. In the period of the first industrial revolution, there you can see that at the time, a growth rate of 1% of the economy every year was already a very good growth rate. With the second industrial revolution, the electricity and the automobile, and also new means of communication like radio, we go to 1.5 to 2% yearly growth in the economy, which is already very high. But starting with the third industrial revolution, you see that we achieve still higher rates of growth. So production grows, and the level of manufacturing in every country grows every year. And I always like to say that revolutions are exponential. Exponential in the sense that if you see here the use of energy from the 1500s to the 19th century, you can notice that from the 1500s to the 1600s, almost 1.5 centuries, the level of use of energy is the same. The energy comes from windmills or comes from the rivers. So there is not much that can be done in terms of improving or incrementing the amount of energy use in the case of Britain. But you see here that as soon as the Industrial Revolution starts, then the use of energy grows exponentially. And you can look at many different kinds of indicators, economic indicators, and you will notice always this exponential growth. Here, this line that you see here is actually an exponential curve because the vertical axis has a logarithmic scale. And what you see here is the so-called thermal efficiency of steam power. So you can see here that when steam power was introduced, the thermal efficiency was under 1%. That means that less than 1% of the heat generated by the machine, by this steam machine, was actually converted, transformed into work that could be transferred to the material. And as you can see, the thermal efficiency has grown over the years, and then in the middle of the 18th century, thermal efficiency was already above 10% and still growing. So this is an exponential curve. But the important thing is that this exponential curve has a doubling time of 21.5 years. So that means it takes almost a generation of workers before the machine you are using is twice as powerful as it was before. Now, if you look at transportation, where we also have exponential improvement of the speed of transportation, you can see here in blue the speed of transportation on land. So this is terrestrial transportation, and in red is air transportation. We have also a logarithmic scale on the vertical axis, so that the blue line is actually an exponential curve. And you can see here that from the 1800s, where a speed of 20 miles per hour was already very good for example, for a locomotive, then up to the 1900s, the speed of a locomotive can go above 100 miles per hour. For air travel, the speed grows even faster because the first air travel vehicles are just balloons. And then when planes start being produced, then you can see that the speed grows very fast. The doubling time for the speed of transportation on land is 34.5 years. So and I wanted to point out these doubling times because what happens in the first two industrial revolutions is that we have, of course, many changes, exponential growth, but it takes almost one generation of workers until you have to change the machines, until you have to remodel the factory. So that the old generation of workers is not as affected by change as it is today. Now, the greatest effect of industrial revolutions has been on the lifespan of humans, so the life expectancy of humans. Here you can see that from the 1500s up to the 1800s, the life expectancy at birth, this is at birth, of people in different countries in Europe was around 40 years because of the many children that died at that time. And you can see here that in this century, the life expectancy in most European countries is above 80 years. So we have duplicated the life expectancy at birth during the three industrial revolutions. And I think that's the most important effect because we have doubled our time on Earth in this way. Now, I was telling you that in the past two industrial revolutions, one machine generation, if you want to talk about machine generation, more or less corresponds to one human generation. That means that the doubling period, as I explained for these simple examples that I show you, allow a generation of workers to finish their life working with these machines, and then the new generation of workers has to adapt. This has changed in the 1970s, and it has changed because of Moore's law. That means that we have so-called core technologies today, and the core technologies have exponential increases in computing power, in the storage, in the amount of bits that we can store in hard disks or in memory, and the bandwidth. So that means the amount of bits that we can transmit per second using the communication means that we have today. The adoption of the new basic innovations is also faster. So in economics, there is something called the basic innovations. A basic innovation is, for example, electricity at home, that you have electricity in your home. It took almost 100 years for almost all households in the US to have electricity at home. Another basic innovation is the telephone. It took almost 100 years for the telephone to be deployed everywhere in the US. Another basic innovation is the automobile. It took like 80 or 90 years before most of the Americans had a car, and so on. So you can look at the basic innovations of the past, and you will see it took almost a century for these basic innovations to develop. The basic innovations that we have today are something like the internet or the smartphones. That's also a basic innovation. The smartphone was invented in 2007, and in 2016, 77% of the population in the US had a smartphone. So that's an amazing rate of adoption. That means that in only 10 years, you have multiplied by a big factor the number of devices that were around during the first years. The same happens with tablets, the same happens with broadband for internet communication. You can see here the numbers. Most of the American population has access to these basic innovations, which are really very, 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 very new, very modern. Now, this has consequences, and I will show you some of them. So then let me talk about the third computer revolution, the one we are now in the middle of. And this computer revolution has been powered by the computer, but mostly by computer chips, by lithography, what's called lithography. And here you can see one picture of the structure of a computer chip taken with an electronic microscope, and the colors are are fake colors, so the picture has been colored so that you can distinguish the different communication lines here on the chip. And but the amazing factor is that the companies producing these chips, they have been able to decrease every year the size of these transistors and increase the number of transistors that they put on a chip. And there is a reason for that, and it's the technology roadmap. The semiconductor industry in the US and in Japan and in Europe, they have a roadmap they update every year. And this roadmap establishes jumps or generations of devices that advance. From example, from 97 to 99, there was a jump of one generation. Then to 2002, there was another jump, and so on. And they developed this roadmap 10 years in advance. So that they say we are going to use 250 nanometers for our chips, and that was in 97. But in 2011, we will be by 50 nanometers for the line width of in our chips. In 2014, we will be by 35 nanometers. And the memory chips will have these capacities measured in bits, 256 gigabits by 2014, and so on. How many transistors will have a microprocessor? By having a roadmap in advance, they can synchronize the product cycle. They can synchronize research. They can synchronize material testing. They can synchronize all the tricks that you need today in lithography, because now we are not talking about 35 nanometers for the line width of chips. We are talking now about 3 nanometers. So IBM is talking already about having 3 nanometer line width chips within the next years. And that's an amazing rate of improvement, which is possible because of this synchronization, because of this technology roadmap. Now, what happens with the technology in terms of computers, that we have gone through several paradigms, different paradigms. The 1960s was the age of the mainframes. Like, for example, the IBM System 360, which was one of the first commercial computers, which were really useful. But then at the same time that we have this decade of the mainframe, there is a new development, usually a decrease in the size, an increase in the density of the chips that are used for building these machines. The new development were the mini computers, the so-called mini computers. So that in the 70s, we have the age of mini computers and time sharing. So time sharing means you only have one computer, but you have many terminals connected to that computer. And one popular computer at the time was the PDP-10, produced by companies that nobody knows today because they all disappeared, like Digital Equipment Corporation. But these were companies which were very important at the time. And this is a time where people start thinking about personal computers. It's the age of mini computers, but people are already thinking about mini computers. And then there are two concepts that I wanted to present to you. There is something called the technology push in when you talk about technology. Technology push means there is no demand for your product yet. You invent your product, you bring your product to the market, and you offer the product, even if there are no consumers that you are aware of. And this is, for example, Ken Olsen. He was the chairman of the Digital Equipment. Digital Equipment was the king of mini computers, but he said at the time when the microcomputer was offered to him, who needs a computer at home? So he just didn't see the need for that. But there were other companies, other people who saw the possibility of pushing the technology into the home. And that was Apple. Apple produced one of the first microcomputers. This, as you can see here, it's a very simple device at the time. And once they offered the computer, once they did the technology push, then they generated demand. So once you are successful with the technology push, there is something else. There is the demand pool. Then there is a demand in the market, and it pulls so that other companies come into the market, like IBM did in 1981. So this first computer is technology push. this next computer is demand pool. This is something that the market is demanding for offices, for using the computer in the office. Now, the logic always in the computer market is that you do the technology push, you offer the product, then there is some kind of killer application that makes that your product is required by the population, at least demand pool. In the case of the Apple II computer, it was VisiCalc, which was a spreadsheet program. So just being able to use spreadsheets was a big improvement, and this generated the demand that made the Apple very popular. In the case of the IBM PC, it was Lotus 123. That was the most popular program for this machine in the 80s. It was a spreadsheet plus database plus word processing, several things in one packet, like Microsoft Office today. And they generated the necessary demand pool that made the IBM PC the most important computer at the time. And so we always have both things in information technology push and demand pull. And one second example for this is the internet. So the internet has been around since 1969. So there was already email in 1969, the first emails. And I had my first connection to the internet for exchanging email in the 1980s, around 1986 or something like that. And at the time, my colleagues at the university were not interested in those connections. They were always making fun of me because I was telling them how wonderful the internet is, and they couldn't see an application. Then the World Wide Web came with the browser, with the visual browser, and then everybody could use the internet suddenly. So you just had to click on the information and the information would be there. This was in the 1990s, around 1993, 1994. This was the killer application, the World Wide Web, the first visual browsers for the internet. And then suddenly everybody wanted to be on the internet. Now we have billions of users. And I can still remember that at the time, I used to give talks, popular science talks, to people who just wanted to know what's the internet. How do I get the internet at home? How do I connect my computer to the internet? So that you see how the world was changed in just a few decades. In the 90s, we have another basic change related to computers. So we saw that there is a paradigm, the mainframe, then we have the age of the mini computer, then we have the age of the microcomputer. But in the 90s, we have something new, which is global networking. And the basic change is that we go from telephone connections where you connect one person with another person with a dedicated line so that they are using a complete connection from point to point, and they are using that connection for minutes or hours. We went from this to packet networks where your speech for the telephone is compressed in a packet, and then the packets are sent from one person to the other, from one node to the other. But you share the communication channel with thousands, even millions of users, and that made the cost of communication go down exponentially fast. So in the 90s, you still had to pay for a telephone long distance call from Germany to Mexico, something like 3 euros per minute. That was at the beginning of the 90s. Now it's so cheap that they don't care about charging you for the use of the communication channel for transmitting speech. They try to make you use video, other kinds of more other kind of applications where you need more bandwidth, and then they try to sell you that bandwidth. The telephone, sending telephone speech is now almost happens almost for free. Now, the introduction of this packet switching was also very interesting for computers, because now computers could exchange all kinds of information. So that in the 90s, you have the convergence of telecommunication and computer technology. The two things become the same thing using these networks. And then there is a third concept that I wanted to talk to you about. So we already saw that there is the technology push that startups usually do when they bring a new product, and there is the demand pull from the market. But there is something else which is peculiar to the information economy, which is what it's called the network economies. If you have a toaster at home, you don't care if your neighbor has a toaster. The usefulness of your toaster does not increase if everybody in your neighborhood has a toaster. But if you have a computer and your neighbor has a computer and another neighbor has a computer and so on, and then suddenly the cost of communication is very cheap and you can connect all these computers, then you can start exchanging information. So your computer becomes more valuable. So the computer is the only thing that you can have on your desktop, and every day you come to your computer is more valuable than the day before because of the information you can access. This is called the network economy, where things become more valuable just as time goes by because of the interconnection of the different devices. So this is what would be a diffusion model for the computer age. Usually what you can observe in the computer age, in this third industrial revolution, is that 10 years before you arrive to a new paradigm, there is a technology push. Someone invents something, like the microprocessor or like packet switching. Then there is a killer application which produces the necessary demand for this new technology. This is the demand pool that you get from the market. Then you get standards. So you generate a standard without having to sit in a committee to agree on some kind of communication standard. Then standards just arise because there are some companies who are the leaders in this market. And then the network economies play a big role. And unfortunately, this leads to monopolies. So monopolies in the information sector are very common, and you all know the companies. Apple and Google and Facebook and Microsoft, Amazon. So it's five. It's the big five, what they call the big five in the US in information technology. And I was just commenting to Joaquin just a few minutes ago that they don't even let other companies, small companies, to become bigger as competitors. They just buy these companies so that they don't get to have competition. And then you have the paradigm shift. Then you have something really new, something qualitatively new that qualifies as the next computer generation. So this is, in a nutshell, what I told you. The 60s is the age of the mainframes, and the basic innovation that happens 10 years before is the invention of the transistor in 1949. Then the 70s is the age of the mini computer. The basic innovation are integrated circuits, not isolated transistors. The personal computer in the 80s, but the basic innovation is the microprocessor in the 70s. Network systems in the 90s, but the technological innovation that makes this possible is packet communication. And in this century, you have mobile devices. And the basic innovation is now that we have cellular telephones able to act as computers, use the communication channels for computers, and then it's a whole new game in the computer industry. Now, this is what has been happening in the last 30 years. So if you look back and then you think, what happened in the last generation? So a generation is like 25, 30 years. What are the most important changes during the last 30 years? One of them is the internet. The internet just happened. And then the second one is what I call Moore's Law 3.0, which would be intelligence on demand. So artificial intelligence happened. Not just Moore's Law. Moore's Law has been around for more than 30 years, has been around for many, many decades. I'm going to show you a picture about that. But now we have something else. It's the convergence of exponential growth in the hardware, or exponential increase in the powerfulness of hardware, but also of software. And the two things are converging. Here you have Moore's law, the classical Moore's law, starting from 1971 with the first microprocessors from Intel up to 2011, and you can continue the curve. This is just the transistor count, and Moore's law, what it says is that every 18 months, more or less, the number of transistors on your chips increases by a factor of 2. There is a doubling of factor 2 in just 18 months. So remember that I showed you that for steam engines, for locomotives, the doubling time was 25, 30 years. Here you have doubling time in the technology of just 18 months. That's a big difference to the other two industrial revolutions. Here you have the data from 85 to 2015. We have had 20 doublings of transistor density. That's 1 million more transistors per chip, a factor. So it's a factor of 1 million more transistors per chip. So whatever you had at the time in density, in chip density, a number of transistors per chip, you have to multiply that by 1 million, and that's what we had in 2015. Now, I told you about software. Software is going faster than Moore's law in terms of algorithms which are important for numerical computation. Not every software. I'm not talking about every program that you can have in your computer, but numerical computation, which is very important for simulations, for developing products. And here you see some of the algorithms that are important. One of them is optimization, linear optimization, or solution of linear equations with the Gauss-Seidel method, optimization with the conjugate gradient methods. And here you see how many years have passed on the horizontal and the rate of increase of performance of the algorithms, just the algorithm, just the code, not the computer. And you can see here that if you paint in green the exponential increase of Moore's law in chips, then some algorithms have grown faster than Moore's law. This would be Moore's law 2.0, so for algorithms. And then something interesting happens. So if you made this experiment, you took one of these algorithms, for example, for linear programming, and you took one of the latest algorithms for linear programming, and you ran that algorithm in a computer from 1991, top of the line in 1991. Or you take the algorithm of 1991 and you run it in 2018 when this experiment was made, and run it in the fastest GPU, the fastest parallel computer that you can have in your at your home, no, in a GPU, and you compare the running time. The older computer is faster by a factor 400. With the algorithms of today, is faster than the hardware. Okay, and people in electronics are always surprised by that. People in mathematics, they love this result because they say, look, it's not just the electrical engineers who are developing faster and faster machines. Also from the side of mathematics, the algorithms we're introducing, they are faster every day. And I think this is an amazing comparison, and one that mathematicians like very much. But GPUs are going even faster than just plain transistor computers with one microprocessor with a few cores. Here you can see that in the last years, Moore's law has kind of becoming slower. So not so slow as this graphic pretends. I think that is still going well with the increase in computing power by Moore's law, but GPUs are even faster. So GPUs increase their performance sometimes from year to year by a factor 10 or sometimes by a factor 100, because you can put a lot of processing cores in these GPUs, and you can see that in the computing cards sold by NVIDIA, the company NVIDIA, how powerful they become from year to year. And then if you combine all these things, so if we now start talking about artificial intelligence, and you take a mixture of GPUs, so fast parallel computers, and the computers of today, controlling those GPUs and the algorithms of today, which are faster and better, well understood than before. And you combine that and you mix and mix it well, then you get AI. So that's what happens when you have all these conditions in place for developing your algorithms. So let me then start talking about AI, because I think this third computer revolution or industrial revolution is about the computer, but in the new phase, it's about artificial intelligence. And artificial intelligence in German, curiously, it's abbreviated not AI, but KI, so for künstliche Intelligenz. But that's also the abbreviation for künftige Informatik, so the informatics of the future. And that's what people say in Germany using the acronym. It's informatic of the future. Now, people talk about two kinds of AI. Strong AI is when you want to build a machine that can reason like a human. So you want to copy the way humans think, and you want to see if this is possible with a computer. Weak AI is a little more humble. You want to perform better than humans, but not in all domains, just in one single domain, like chess, for example. So you just say, I'm going to build a computer that can beat the world champion in chess. And then you do it. So in the 90s, the computers defeated the world champion in chess. Or you say, I'm going to build a computer that is better than humans at integrating functions or differentiating functions. And now Mathematica can integrate and differentiate functions much better than humans can do, and so on. So there are many fields where you can really try to be superhuman, but it has to be a closed domain. And this is it's called weak AI. So you don't try to solve everything. You try to solve one problem. There are three approaches to artificial intelligence. One is the symbolic artificial intelligence, which is based on logic. So you write rules, and these rules tell you that if this and this and this happens, that you can make an inference about the world or about a closed system that you are inspecting. It could be mathematics. You give the actions to the computer, and then the computer can prove a theorem, or can see if your proof is right, if you follow all the right rules and use the right actions for your proof. Sub-symbolic AI is neural networks. It's based on neural networks, or it's called pattern recognition. There are many names for sub-symbolic AI. In sub-symbolic AI, you don't give rules to the computer. You present the computer with examples of what you want to achieve, and then the computer builds a statistical model of what you want to do. And there is also the probability-based artificial intelligence, where you want to get probabilities. You want to get from the computer an answer about what does the computer think that something is going to happen. Like, for example, weather forecast. So if you get a weather forecast of rain, you want to know what's the probability of rain tomorrow, not just that it could be that it rains. In the case of symbolic AI, you can ask the computer why. So if the computer tells you this is going to happen according to these rules, then you can ask the computer, why is that? And then the computer can go back, show you the rules, and explain you the result. In the case of symbolic AI, usually there is no explanation. So these are statistical models, and then you get an answer. The computer says, yes, this is a face, or this is a horse, this is the image of a dog. But it's difficult to get an explanation. And many research projects nowadays are trying to get those explanations also from sub-symbolic systems. But we are still at the beginning, so we are not yet there. So just remember, so we can do AI based on rules, AI based on neural networks or statistics, or AI based on probabilities. And then we don't want to program these systems by hand. We want these systems to learn by themselves, like if they were children and we are teaching them how to do things, and then they learn the rules, or they learn the patterns that they have to recognize. And there are three kinds of learning. There's supervised learning, where you have a database, a labeled database of faces, for example, or images, or horses, or dogs, and then you train a neural network to recognize the different kinds of images. Unsupervised learning means you don't have a labeled database. You want to inspect the database to see if there are patterns inside, if there are clusters that separate some kind of data from other data. This is what's called data mining. And self-supervised, which is, I think, is very interesting, and it has been used now in the last years for many kinds of applications, means learning by doing. So you don't tell the computer how to solve a problem. The computer learns to solve the problem by playing against itself. For example, playing chess against itself. So you don't tell the computer, maybe you give the computer the capability of looking at different moves and the tree of different moves that you want to analyze, but you don't tell the computer how to weight the different possibilities of the different chessboards. The computer should learn the so-called cost function by itself, and the computer can learn it by playing against humans, or can play computer against computer, and then the computers become better just by playing between themselves, like the system AlphaGo from Google. So AI is a moving frontier. This is what I always tell people when they ask me, what's AI? So AI is a moving frontier. Yesterday, it was computer algebra. Still in the 80s, computer algebra was a project in AI. Chess playing was a project in AI in the 90s. Playing the game of Go was a project in AI 5 or 6 years ago. Recognizing speech is still a project in AI because the systems are not yet perfect, but they are much, much better than what you could see in the 80s or the 90s. Everybody wants to translate documents, and several translators are very good, but we would like a professional level translator. Until the computer is better at translating documents than a human, it will take several years for this to happen, and so on. So you can put here your favorite domain, and then you can think, is this possible with a computer? Yes or no? How many years will it take? And then you can go and start your company, do your startup for solving this problem. And I think every time that we think about intelligence, we shouldn't think that intelligence is just human intelligence. So it's everything between nothing and human intelligence. There is the intelligence of plants. Plants have a certain intelligence because they can react to the environment. The invertebrates, they have an intelligence, the fish, and so on. And then you have like phase transitions between the different kinds of animals. Like, for example, pain. So if you ask, and I have done this at the university, that I ask my students, do you think that plants feel pain? And probably not, because they don't have those sensors for feeling pain, but invertebrates already feel pain, probably. Are invertebrates aware of themselves? Probably not, but maybe reptiles already have some kind of awareness. Do fish have emotions? Yeah, probably not, but mammals could have emotions, and so on. And the humans are the only ones with reason, which was called logos in Latin, and that's why we talk about logic, because it's something inherent to humans. So there are many kinds of AI that you can do if you decide to have some capability for your machine. If you want to be better than a fish, for example, with your robot in water, then you need to have some kind of intelligence. Okay, so now let me go to an example. So now I'm going to show you an example, which is transportation. How do this industrial revolution manifest itself as a mega trend in the field of transportation? If you look at transportation, people talk about four mega trends. One is electrification, going to electric cars. The other is connectivity. The other is new schemes for mobility and autonomous driving. And I'm going to show you some statistics and some things that have happened in the last years in this field. First, electric cars. So there are several companies who already announced they are going all electric. So they are not going to sell gasoline cars beyond the dates that you see here. So for example, Jaguar in 2025, Bentley in 26, Cadillac in 30, and so on. Volvo in 2030. And if you see, these are very expensive cars. Also the Volvos are expensive. So the first companies going all electric are the expensive car companies, like Tesla. Tesla is very expensive. The luxury cars, because electric cars are still more expensive than gasoline cars. So it makes sense for the cars which are more expensive to go all electric. But Volkswagen already announced that in 2026 they will have the last development of non-electric cars. So that means they will start producing or researching how to build the last gasoline car, and they will still sell gasoline cars for a few years. But in the 30s they will go all electric. And Ford will go all electric in Europe in 2030. Not in the US, but in Europe. So you can see here this trend is materializing. This means that we have to modify the cities. We have to do city planning, because if you live in the 10th floor of a big building and you want to charge your small car, electric car, then where do you charge it? And one example here is from Berlin. So this is a picture from Berlin where the light poles can be retrofitted for charging cars, and this is one alternative that is being proposed. But the really good alternative would be to just not have the cars on the street, park on the street, to have buildings for parking the cars in those buildings for every block in the city, and then have the charging stations within those buildings. And this is already being planned for new quarters in Berlin, which are being built today. They will not have cars parked on the streets. All the cars will go to a parking lot or parking building, which is in the same block where you live. So that you go there, you leave your car, you charge your car, and then you walk to your apartment. There's a big problem with trucks. And the big problem is that the electric batteries are very, very heavy. So if you don't want to have a very heavy battery in an electrical car or a truck weighing for the 4 or 5 tons, what you can do is you can have these so-called trolleys, and then the electric vehicle can charge itself from these power lines. And if the car has to overtake, then the trolley goes down, and there's a small battery. So there's a battery, but a battery that allows this vehicle to go autonomously from the power line, like 5 or 6 kilometers, and then it has to reconnect again. So this is possible, and this is a test bed in Berlin where they are testing this technology for the future. Okay, so this was electrification. Now, schemes of mobility. This was a simulation that was done in New York using real data for taxis. They took the data from 150 million taxi trips in 2011, and then with a computer, they did this experiment. Instead of just picking one passenger and going to the end, they had the data for all passengers at that moment, and then they simulated in the computer that the taxi collected one passenger and then another one along the way, so that you had 2 people in the taxi. The first person has a certain loss of time because you have to go and pick the second one, but they are going more or less in the same direction, so that the loss of time is not very, very big. And this is the result. So if we bound the time lost by the first passenger, and we only have 2 passengers per car in a shared taxi, we can save 50% of the vehicles in a city like New York, which is almost perfect. So 2 persons in one taxi mean you only need half of the cars that you had before. If you put 3 persons in the vehicle and you bound the amount of time lost by the first passenger by 300 seconds, that's 5 minutes, then you can save 60% of the cars, a result which is almost also perfect. That means if we use computers to organize traffic and to organize the passengers that are picked, then we can really optimize traffic and we can reduce the number of cars in the city. Now, connectivity, the third mega trend. So cars of the future will be connected between themselves, will exchange data because the standards are in place. the law that will make mandatory for new cars in the US to have this connectivity has already been prepared. It's being discussed in the US. At some point, it will be enforced, and then every new car produced or sold in the US will need to have communication between cars and between infrastructure. So that means that before you arrive to the traffic light, you know if the traffic light is going to be green 10 or 20 or 30 seconds because of this telecommunication. And then you can adapt your way of driving to this information. If you're arriving to a corner, then your computer will tell you that there is a car coming across your way, and then you have to be careful. These kind of things for safety, they will be available in all cars. And something else will be available. There's a new law for autonomous cars in Germany, and they require the new cars, all new cars which are autonomous in Germany, they will need remote operation. That means if the car or bus or whatever is empty, is traveling empty or without a driver, and arrives to some point of the city where it doesn't know what to do because it has to break the rules. Let's say that there is a construction site and the lanes are blocked, and then you have to go around the construction site using the other lanes. So that means going against traffic. Then the autonomous car is not allowed to do that. Has to ask a person to give the green light, and then it has to connect to a remote operator, and the remote operator looks, says it's okay, then do this, or even takes control of the car by itself, and then those what is required. Okay, so telecommunication will be very important for all these vehicles. And then autonomous driving, which is one of the projects I have been working in the last years. And I always tell people that we are not in the past. The past was when the driver was in charge of the complete vehicle. We are now here in the middle, where the computer is a co-pilot with the driver. So there are many cars today that can stop if you're going to crash against something, or cars that control or monitor what you are doing in curves, and then make sure that you don't slip on the curve. And this is where we are going. We are going to a situation where the computer takes over and then controls all the electronics in the car. So my definition of autonomous car that I always tell people is an autonomous car is a taxi, but the taxi driver is a computer. And this happens already today. So many people think that when they take a curve, they are fantastic drivers because they can take the curve very fast. But what really happens is that the computer is monitoring the speed of the different wheels. And if the circles that the wheels are describing are not concentric, that means that one or two of the wheels have lost the grip on the surface. And then the computer breaks those wheels and makes sure that all the circles become concentric so that you don't sleep on the highway. So the computer already makes you a good driver. This is the future of transportation. No cars park in the city. All cars are distributing people in the city or are being charged in special parking lots. And the vehicles are fully automated. So in the field of autonomous driving, we talk about levels of automation. Full automation is level 5, according to the definition of the automotive engineers. And high automation is for the highway, where you can take your hands off and then the car makes almost everything by itself, but you still have to intervene now and then. And conditional automation is where you have to be really aware of what the car is doing, even if the car is keeping the lane by itself. And this is where we are today. We're in between 3 and 4, more or less. These are the cars being sold today. Going to full automation to really level 5 is a big step in technology. But it will happen. And these are the statistics for the companies active in California. I just want to show you the statistics of, for example, Waymo. It's a subsidiary of Google. Cruise is a subsidiary of General Motors. And they say they can drive already 30,000 miles before the safety driver has to intervene. For Cruise is 28,000 miles and so on for the different companies. It's a little misleading because they don't really drive 30,000 miles before the computer asks you to intervene. because the safety driver can intervene before. If a safety driver thinks, oh, there is a child on the street and I don't want the car to come too near to the child, and the safety driver can intervene. And this is not here shown here in the statistics, but still, it's an amazing statistic, and you can see here the amount of kilometers that these companies traveled last year, more than 1 million kilometers for Cruise and almost 1 million kilometers for Waymo, so that they are advancing the technology. There are many challenges for this technology, which I'm going to skip so that I come to the end of my talk. So what I want to show you is that we have had industrial revolution since 2 or 3 centuries ago. And every technological revolution is different in the sense that we have different basic innovations, a different basic technology that is being used. The basic technology now is the computer. The rate of change is sub-generational. That means that's a problem for training the workers today so that everybody loses their job. But these paradigm changes that I described to you that happen even in intervals of 10 years mean that for me, 2020 to 2030, the new paradigm will be intelligence on demand. That means this is something like Maker's AI. So you remember that it was very difficult to put a computer in every product years ago. But now there is Arduino and all these tools where you can, without being an electronical engineer, you can put together a small computer for doing something with your equipment. Well, it will be the same with AI. There will be tools for putting intelligence in every product, for putting intelligence, speech recognition, face recognition, and many other things in every product. So that I think this decade will be the decade of the Internet of Things, like people say, the Internet of Smart Things, which is still a new phase of development. Okay, so we still have a few minutes for questions. Thank you very much, Joaquin, for the invitation, and I can answer your questions now. Thank you.
Contrary-wise, Raul, thanks for your amazing talk. We have quite a few questions from the audience. Juan Bautista is asking, well, you are describing this situation with an exponential growth in technology, but there are many countries, including Mexico, that seems to be a little bit left behind. What do you think is the role for the different countries in this revolution?
Yeah, that's a difficult question because Mexico is being left behind, not so much as a consumer, but as a producer of the technology. So many people ask me always, when will autonomous cars arrive to Mexico? And I always tell them they will arrive at the same time as in the US because the cars will be produced in Mexico, like they are produced today. So we will have those cars here. But then you have the problem that the infrastructure is not the infrastructure that you have in the US, for example, highways or in the cities. And these cars will be developed for streets which are in good shape, streets where every line is painted and so on. Then we will need to change that in Mexico so that we don't have streets that look like some streets that we have. So that's a real problem. But the bigger problem is that the technology is being produced in other countries. So the research centers are in other countries. Even if we consume, if we arrive at the same time to the product, the technology is there. And that's one of the things that worries me for the future.
Thank you. Jorge Huerta is asking, what do you think about the capability for the general population to assimilate these rapid changes? It seems like, what's your opinion about this?
Well, as consumers, as I said before, everybody is very happy to buy the newest smartphones and so on. As producers, we have a problem in research, and the other problem is we will not need so many workers because the Mexican factories are also being automated. For example, the new Audi factory in Puebla is one of the most modern that BMW has. And they even train workers for German factories. They send them to Mexico to be trained in the new factory so that they can come back and work here. And so that's a problem. It's a universal problem. It's a problem in every country. As I show you, in the US, less than 10% of the population is already producing everything you can touch. If we come to that kind of number in Mexico, then we really have a problem because we have to provide work for those people. And we already don't have enough work for everybody. So 50% of the Mexican workers are informal workers. So that's one social problem that is very difficult because it combines many different factors in Mexican life.
Right. Now, in terms of the planet itself, exponential growth demands exponential resources, no? And we live in a planet with limited resources. How do you think this situation will resolve?
Yeah, that's a very good question. So I didn't show you that because that was one of the slides that I skipped. People talk today about a technological singularity, where exponential growth becomes almost continuous. But there are two breaks to exponential growth. One is the environment. So we are seeing that with climate change. And the other one is we have to provide work for everybody. So that's also a break, a social break. There is a social break and there is an environmental break. And we have to be aware of that. And in the case of energy, for example, it's very good to go to electric cars, but it's even better if the electric cars are being charged from renewable energy sources, from solar or wind or hydroelectric, not from fossil fuels. So everybody's trying to get away from fossil fuels except Pemex, but everybody else in the world is trying to get away from fossil fuels in order to avoid this. That if we are talking about exponential growth, we don't want to have exponential use of fossil fuels, and the best energy is the energy that is not used, is the energy that is saved. So savings in energy are also very important, and Europe has been doing many things about construction because the main source of consumption of energy in Europe is for heating houses. But if you have good materials, if you have good isolation, you can save a lot of energy. And so Europe has been doing also a lot of things in this sense. So I agree. So we have to be aware of the environment, of the social problems, and these are going to be breaks on this exponential growth.
Okay. Well, Raúl, I thank you on behalf of the ICASAT 2021. I want to thank your participation in the conference. Your talk has been very illuminating. On a personal note, I think your opinions are like a lighthouse, and I will invite you to keep raising your critical voice whenever you see space for improvement. Thank you very much, and I wish you the best of luck with your new endeavors. Thank you.
Thank you. Thank you, Joaquin. Thank you, everybody, for watching this talk. Sehen wir noch live?